This is lecture 3 of the course on finite group theory, a pure math course at junior senior level, and the main author, first author of the textbook for this course. Here's the textbook. It's in the Teach Yourself series called Mathematical Groups. For details on how to get the book, its price and that kind of thing, go to this website. So profhugodegaris.wordpress.com. And lecture 3, the topic for this evening, because I record these handycam lectures in the evening, usually around midnight. So the topic is binary operations. So I'll start with explaining what a binary operation is, or rather what an operation is, or what an operator is, and then say a little bit about how it's relevant to group theory, because that's what the course is about, group theory. So some of the things that we will learn in this lecture are directly relevant to defining the concept of a group. Now a group is a particular kind of set, and it has a very rich structure. So using the axioms, the foundations of what a group, the definition of a group, you can build whole cathedrals of mathematical logic. It's a very beautiful and powerful subject. It's one of my favorites for sure. Okay, so let's start with the concept of an operator. What is an operator? Well, they pop up in math and physics all the time. For example, in quantum mechanics, in physics, the very foundations of quantum mechanics uses the concept of operator. So what is an operator? Well, think of it as a kind of symbol that tells you to do something, right? So since grade school, even kindergarten, you're probably familiar with this operator, this symbol. This cross. Now you know it as the plus sign. And what's its meaning? What does that symbol instruct you to do? Well, to add things, to add two numbers. Okay. And what are some other obvious operators that you're familiar with? Well, minus. You just the minus sign, so you subtract two numbers. And of course, well, let's go through the arithmetic operators. This way, like that's to multiply, or if in a computer guy, it'll be like the plus and that together. So 1, 2, 3, 4 would be like a star or an asterisk. That's the multiplication, the multiplier operator, the symbol that instructs you to multiply two numbers, two things together. Divide. No, it doesn't have to be arithmetic type operators. There can be other operators. Like for example here, a to the b. So you take the number a and you raise it to the power b. So you're operating on these two numbers to give you this result. Okay. So let's now talk about binary operators, and as contrast, unary. So binary, that's an operator that operates on two things, by two, right? So a binary operator operates on two numbers, whatever, two things, and a unary operator operates on one thing. So what's an example of a unary operator? How about square root? Okay, that operates on just one number. So if you apply the unary operator, the square root sign, that's a symbol that tells you to do something. Take the square root of 9, for example, and your result will be 3. Okay? Or how about the square? So the square is a 2 raised, so a power. So to square a number, say like a squared, you just multiply by itself and you'll get the result 9. Okay? Now we can generalize. So you take two things two members of a set, let's say. So let's say you have a set S with members, and you can apply a binary operation, for example, plus, minus, whatever, and its general form, the symbol of a generalized, abstract, if you like, binary operation, is a little circle, like this. So you take any two members of your set, say A and B, of your set S, you apply this binary operator on the two of them, because the binary operator, you need to operate on two members of your set, say A and B, and you get a result. Well, hopefully. If you don't get a result, I mean, if no answer, if no result is defined, if it's not well defined, then this little circle here, which is a symbol for a binary operator, generalized, then it's not defined. You have to get a result. And to be a binary operator, this result, by definition, we'll talk a bit about here, like conditions for a binary operation, this result here has to be just one of them, one and only one result. Right? If there are more than one or zero results, no results, then this operation, this binary operator, is not defined. Right? So for it to be defined, the result here, result of the operation, there has to be one and only one result. Okay? Alright, now, so that's the two main conditions for a binary operation, well, as defined in the textbook we're using. Other authors are somewhat more flexible. But, so one is, when you perform a binary operation on any two elements of your set, so A and B, two members of your set, you get a result, and that result, there can only be one and only one of them. Okay? And a second condition is that result has to belong to the same set as A and B. And if that's the case, if for all, put it in technical terms here, now you're probably familiar from, was it last lecture? Lecture before? Anyway, forgetting. This is the for all or for every sign. So it's like a capital V with a wiggle. So this is the for all. You've probably seen this before. For all or for every. So for all elements A and B belonging to your set, you perform the binary operation on those two. So A, binary operator, little circle. B gives you a result C. Then C belongs to the set. If that's true for all possible pairs A and B, then this binary operator here is said to be closed on the set S. If you draw a kind of Venn diagram, so this is your set S, and there are any two elements A and B. If you perform a binary operation and A binary operator B and you get a result C, then that C belongs to S. Right? So this binary operation is said to be closed. So what it does not do is produce a result that's outside the set. So in a sense, in a manner of speaking, imagine a kind of fence around the set in the Venn diagram. So in a sense, all the results lie within the set, right? So in that sense, this set is closed. Like the results can't get out, right? They're inside the set. So that's why this term closed is used. So closure is this fact. The binary operation gives you a result that's always in the set. Okay, so closure is a very important concept for groups when we come to do that in 2 lectures' time. So so closure. So here's the definition of closure. For any two members of the set, you perform a binary operation on them, little circle, whatever it is. It's an abstract, generalized concept. you get a result C, and the result has to belong to the set. So that's closure. Okay, here's some examples. Now notice in general, I'm putting a set here, like in abstract form. So we've got a set S and a binary operator